Hello everyone. So today in this video, we will be talking about isotopes and applications. First of all, we would be discussing, the meaning of the term isotope. Then we will be talking about different types of isotopes and, different examples of isotopes. And last, we will talk that what is the need to study isotopes, what are its various applications. So let's, quickly move on to the, topic. So if you look at the, diagram, which is there on the left, see, in the center, what you will find is the nucleus. Yes, nucleus. And inside the nucleus, you all know that there are two types of subatomic particles present, that is proton and neutrons. And in the outer orbit, electrons are revolving. Okay, so now the question is, what are isotopes? See, basically, if you look at this figure, which is there on the extreme right, see, I have shown three diagrams over here. One is for carbon 12, one is for carbon 13, and one is for carbon 14. Now, what is the basic difference between these three? If you carefully look at them, it is containing, carbon 12 is containing 6 protons, it is also containing 6 protons, and it is also containing 6 protons. So now what is the difference? The difference lies here, children. So difference is basically in the neutron. So it is containing 6 neutrons, it is containing 7 neutrons, it is containing 8 neutrons. So basically, if you are asked that what are isotopes, so I think now you can just summarize that they belong to a family. Okay, they are the members of the same family of an element. They are the members of the same family of an element. And but in this family, what is the difference? Is the difference lies in the number of neutrons. Same family of an element they belong to now, but differ in number of neutrons. So if their number of neutrons will be different, now you all know that if number of neutrons are different, then what is different, children? Then mass number is different. See, you all know, mass number is basically protons plus neutrons, sum of protons plus neutrons. Now protons are same in all the three cases, but what is different? This factor is different. So if neutrons are different, then this entire sum will become different. That means mass number will vary. But since their protons were same, so that means they will have same number of electrons as well. And if electrons are same, that means atomic number will be same. So they have a same atomic number. So atomic number is same, but mass number is different. So this is the basic concept of isotopes. They are belonging to the same family of an element. So if I'm talking about carbon, carbon is having three isotopes, carbon 12, carbon 13, carbon 14. But what about their atomic number? Their atomic number is same. They all have the same atomic number, that is 6. So that means if I talk about the periodic table, so if I talk about the periodic table, so in the periodic table, the position will be same. Periodic table, they occupy same position. Okay, so they have the same position in the periodic table. But what is the difference? Difference is in their mass number. Now, although their mass numbers are different, okay, so that means they will have certain unique properties. Even a difference in the single neutron can change certain properties of the element. Okay, so if you look at these isotopes, see, if you look at 12 and 13, in them the difference in the proton or neutron is not too large. Since in 12 it is having almost equal number of neutrons and protons. Here only one neutron is more than proton, so they belong to the category of stable isotopes. Whereas if you look at carbon 14, then you will find that 8 neutrons are there, means 2 neutrons are more. So here it becomes radioactive isotope. So what is the meaning of radioactive isotopes? Radioactive isotopes are the one which decay with the emission of radiations. Means when they decay, they produce large number of radiations like alpha rays, beta rays, gamma rays. So those radiations are produced. So if you are talking about isotopes, so isotopes are basically of two types. We have stable isotopes and we have radioactive isotopes. Radioactive isotopes. If you talk about stable isotopes, in nature almost every element has its isotopes. Okay, so like if I talk about carbon, just now we were talking about carbon. So carbon 12 is stable, carbon 13 is stable, but carbon 14 is radioactive. Although the abundance of carbon 14 is almost negligible, it is very, very, very less. Okay, the one which is mostly abundant in nature is carbon 12. Okay, so that is why the atomic mass which we consider in as per the periodic table, that comes out to be average atomic mass is 12 only. And in the previous video I have explained how we can calculate average atomic masses of the element. Similarly, if you talk about hydrogen, let me show you a very good diagram. See, all of you, please look here. See, in this, if you look here, hydrogen is the only element whose isotopes have been given special names, like here protium. Protium is hydrogen whose atomic number is 1. Obviously, all the isotopes will have 1 atomic number, but mass number is also 1. Deuterium is with mass number 2. Tritium is with mass number 3. Now here, if I talk about which one will belong to the category of radioactive isotope, it is tritium. Okay, so same way you have these 3 different isotopes of oxygen: oxygen 16, oxygen 17, oxygen 18. So this is also one of the example, but since the mass percentage abundance of oxygen 16 is the highest one, okay, so the average comes out to be near 16, and that is why we take its mass to be 16 generally. Similarly, we have 2 isotopes for chlorine as well. We have chlorine 35, we have chlorine 37. So in this way you can see that every element here, though I have included only 3 examples. Likewise, you have isotopes for uranium, you have isotopes for nitrogen, so sulfur, sodium, cobalt. So we have different isotopes for different elements. So but what we need to understand is the importance. Now before moving on to that slide, let me tell you, now you're clear radioactive isotopes. Now what is the basic concept behind these radioactive isotopes? Radioactive isotopes, they are one which decay with the emission of radiations. Now if you'll talk about radiations, what type of radiations am I talking about over here is alpha rays, beta rays, gamma rays. Although they are their radiations are quite harmful, but we have lot of medical applications of these radioactive isotopes. Okay, so now let's talk about various applications. See, isotopes are very important. If we talk about from medical point of view, if we talk about from agricultural point of view, they are very much helpful. Like if you see at cobalt 60, if you look at cobalt 60, it is used in radiation therapy to treat cancer. If you look at iodine 131, iodine is very important for the functioning of thyroid gland. So even it is used to trace thyroid gland disorders like goiter. It is used to locate brain tumors. Similarly, we have an isotope of iron 59. You all know that iron is used, or you can say iron is required for the formation of blood. Now here we are using iron 59 for the diagnosis of anemia, for pregnancy disorders. Same way, sodium 24. You all know that salt is very important for healthy blood circulation because salt contains sodium. Sodium and potassium, they play a very important role in maintaining the blood pressure level. So sodium 24 isotope is used to study blood circulation. Similarly, uranium 235. Uranium 235 is like, it is one of the most radioactive isotope, and it is used to produce energy in nuclear power plants because, it emits large amount of radiations. Similarly, chromium 51, we can use this, isotope to study number of blood diseases. So if you look at isotopes, why they are important to be studied? They are important because they have lot of applications in the field of medical science or in the field of agriculture. So they have, in the field of energy sector. So they have, a wide scope of applications. So isotopes are quite important. Now, in the next video, I'll meet you with a new topic, that is isobars, which is just opposite of isotopes. So till then, bye bye, and take care, everyone. Bye, everyone.